Hi, my name is Jay Young. I'm a postdoc at the University of Minnesota working in commutative algebra, and I'm currently on the job market. Broadly speaking, my research can be split into three major topics: computational syzygies, probabilistic methods, and virtual resolutions. In each of these topics, I blend techniques from commutative algebra, combinatorics, and computation to solve problems. By computational syzygies, I mean the problem of computing Betty numbers of a module, or equivalently, the dimension of the graded pieces of the Tor modules. The usual approach to this is to compute a free resolution of the module, but this requires iteratively computing Grosvenor bases, and as such can be quite slow. Our approach here is to transform this into a linear algebra problem by instead resolving the field using the Kazul complex. In this manner, we've translated a hard commutative algebra problem into a hard linear algebra problem. And then we can use high throughput computing and numerical linear algebra to compute the Betty numbers. Despite this simplicity, this approach has actually allowed us to compute the Betty numbers for many modules. Specifically, we've computed the Betty tables for modules coming from the Veronese embedding of P2 up to degree 6, and in more recent work for the modules coming from the Segre-Veronese embeddings of P1 cross P1. As well, in a current project with Vic Reiner, I've been working on applying these techniques to computing syzygies over the diagonally symmetric polynomials, with a view towards generalizing the n+1 to the n-1 conjecture. Our next topic is probabilistic methods and random monomial ideals. Our goal here is to use probabilistic methods to open a window into the asymptotic behavior of Betty numbers and other properties of ideals. As such, there's two major goals. The first is to understand the properties of a random monomial ideal, and the second is to use these properties to give heuristics for non-random families of ideals. On this front, I've worked with two distinct models of random monomial ideals. The first is a random monomial ideal coming from a random flag complex via the Stanley-Reasoner correspondence. And the second is a so-called Erastus-Renyi type model for a random monomial ideal, where the generators are chosen in a way reminiscent of Erastus-Renyi edge-independent random graphs. So this first model was introduced by Daniel Ehrman and I in a paper where we discussed primarily asymptotic non-vanishing of syzygies. Specifically, we were able to show in some sense that nearly all of the Betty numbers in a large region of the Betty table are non-zero. And more recently, with Caitlin Booms and Daniel Ehrman, we've shown that for almost all choices of parameters, the Betty table actually depends on characteristic as well. The second remark is worth noting because this is actually one example where the behavior in the case of non-random families of ideals is actually not that well understood, even for the Veronese. As for the second model was first described by Delora, Petrovic, Silverstein, Stasi, and Wilburn, and what we've done, again with Silverstein and Wilburn, is to constrain this model, constrain the degrees and more generally the standard pairs of the monomial ideals that come from this model. Now both of these models merit further study, and the hope is that better understanding of these random ideals can give us heuristics about the behavior of non-random families of ideals in the asymptotic setting. Finally, we come to the topic of virtual resolutions. Virtual resolutions were introduced by Christine Berkesh, Daniel Ehrman, and Greg Smith in order to fix the problem that free resolutions of a module over the Cox ring of a toric variety do not always reflect the geometry of the module viewed over the toric variety. As an example, the free resolution can be too long in the sense that it's not necessarily bounded by the dimension of the ambient toric variety. It's still bounded by the number of variables, but not the dimension of the ambient toric variety. The way we fix this is relaxing these free resolutions to free complexes where we allow certain amounts of homology, in particular homology that's irrelevant. And there's much to be understood still about these virtual resolutions, but so far, working primarily in the monomial case, I've been able to show a monomial virtual Hilbert syzygy theorem, along with a partial characterization of virtually Cohen-Macaulay monomial ideals in virtual regular sequences. And this is a topic that we're still actively working on, and we hope that we can give a complete characterization of virtually Cohen-Macaulay monomial ideals, analogous to a Reisner's criteria, along with a degeneration result which would allow us to reduce some statements about virtual resolutions to the monomial case, as is often possible with free resolutions. Thank you for listening.